What's up, guys? Welcome back to Math 18A, College Algebra. It's been a little while since I've recorded the lecture, so I'm feeling a little bit awkward on camera again, but whatever. So today we're going to be starting section 4.2, which is exponential functions. So we finally get to stop talking about polynomials for a little while, at least. And exponential functions are just another way to model like physics problems or financial problems, things like that. So yeah, let's go ahead and get into today's lecture. Okay, so let's first just take a look at the definition of an exponential function. So an exponential function f with base a is denoted by f of x equals a to the x. So here we call a our base. And that'll be more important in the next section, 4.3, when we study logarithms. So for now, just keep that in mind. A is your base of your exponential function. And we need a to be greater than 0. A cannot be 1. And x here is any real number. So let's just take a look at how our function behaves first. So let's pick some value of a and sort of just take a look at what the function looks like. So let's pick a equals 2 first. Then let's take some x values and maybe we'll make an x and f of x kind of table here. So x, f of x, and we'll just see what happens with our values. So let's take some negative values like -3, -2, -1, 0, 1, 2, 3. So this is a technique that we did quite a while ago. We used to make sign charts, or not sign charts, like table of values, right? And so that's kind of a nice thing to just use to understand what your function is doing. All right, so, sorry, it's going to bother me if I have it like that. Okay, let's take a look at x equals -3. Then our f of x here is going to be 2 to the x, right? But we're plugging in -3, so 2 to the -3. And then let's just keep it like that for now and keep moving forward in our table here. 2 to the -2, 2 to the -1, 2 to the 0, 2 to the first, 2 to the second, 2 to the third. And then I'll simplify it a little bit down here. So remember, with negative exponents, I'll do a sample calculation like over here. If you have a negative exponent, you have to take the reciprocal of your base, essentially, and raise it to the third, like the power, but positive. So here, this would be 1 over 2 to the third. And so that's going to be 1 over 2 to the third is 8. So in my table here, this is the same as 1/8 equals. Then the same thing, the calculation will work the same way here. 2 to the -2 will become 1 over 2 squared, so 1/4. This will become 1/2. 2 to the 0, any constant to the 0 power is just 1. 2 to the first, just 2. 2 squared, that's 4. 2 to the third, that's 8. So these are the numbers that we're looking at here. So let's sketch a quick graph, just plotting these points to see what that would look like. I'll graph it in green. So we need 1, 2, 3, -1, -2, -3. And so at -3, I'm 1/8, so that's quite small, very close to the axis. At -2, I'm 1/4, so a little bit larger, not a lot. At -1, I'm 1/2, so again, a little bit larger. At 0, I'm 1, so I guess I'll scale this so that my 1 is right here. At 1, I'm 2, so you can see that it jumps up quite a bit. At 2, I'll be 4, so we can't quite reach that anymore. But it's going to jump up a lot. So it increases very, like, steeply, you could say. And then on the left-hand side here, it's going to approach this axis, this x-axis here, but it won't touch it. Yeah, it shouldn't cross the x-axis here. So that's what this f of x equals 2 to the x function sort of looks like. So generally speaking, if you pick an a that is greater than 1, you're going to have a graph that looks something like this. But now let's take a look at what happens if I choose, let's do it in black. A equals a half, so like between 0 and 1, these fractions. And we'll do the same thing. So f of x equals 1/2 to the x. Let's make a table of values here, x and f of x. And we'll just go ahead and pick the same values. And so you'll notice that it's going to come out very similar, because in the other problem we were already looking at these 1/2 to powers using the negative x exponents. But let's just see what happens then. So sample calculation for the first one, 1/2 to the -3 means that I have to take the reciprocal again, but the reciprocal of a half is 2 over 1, if you want to be clear about it, and take that to the 3rd power. So it'd be like this, technically, but because it's 2 over 1, that's just 2, so just 2 to the 3rd, right? So 2 to the 3rd is 8. And the same thing will happen for these other negative exponents. We'll take reciprocals and raise it to the positive power. So this is 2 squared, this is 4. 2 to the 1st is 2. And now let's look at the 1/2 again. 1/2 to the 0 is still 1. 1/2 to the 1st is 1/2. 1/2 squared, you just have to square the top and square the bottom, the numerator and denominator separately. So 1 over 2 squared is 1/4. And the same thing for this, you'll have 1 over 2 to the 3rd, which is 1/8. And we'll sketch a quick graph of that as well. So let's look at our x values again. -1, -2, -3. And then 1, 2, 3. And at -3, I'm now way up here at 8. So like somewhere, actually, why don't we start on this side because it's going to have to scale. So at 3, I'm 1/8. At 2, I'm 1/4. At 1, I'm a half. At 0, I'm 1. So again, I'm scaling this so that my 1 is here. At 1, I'm 2, so way up here. And then continues to scale very quickly. Continues to grow very quickly in that direction. So my graph will look something like that. So it's kind of just this one, whoops, but facing the other way, right? So it looks like it reflects over this y-axis, actually, which is interesting. So if we take a closer look at this f of x and compare it to our other f of x, let me just go over here. F of x equals 1/2 to the x. And we got, with positive values of x, we have these fractions, 1/2, 1/4, 1/8, which we also get for our f of x equals 2 to the x function. But we get it from the exact same exponents, just the negative versions, right? So another way of looking at this function, f of x equals 1/2 to the x, is actually just taking f of x equals 2, but to the negative x. So here's a general summary of exponential functions, listing the properties and looking at our two different cases that we could have, this a to the x and a to the negative x. So let's go ahead and run through the properties. We'll take f of x equals a to the x, where a is greater than 1. So the domain of this function is all real numbers, or you can write it as negative infinity to positive infinity. Because looking at this function, there's no way that we can divide by 0 or take a square root of a negative number. So we can plug in any value of x that we want. The range is 0 to positive infinity. And remember, the range is the set of y values that your function takes. And so we only take positive numbers here. We'll never cross that x-axis into negative numbers. So that's an important thing to remember about exponential functions. The y-intercept is 0, 1. So no matter what your base is, you're always going to cross the y-axis at 1 and at x equals 0. This function is increasing. So going from left to right, reading our graph, it's always increasing. It's always going uphill. The x-axis is a horizontal asymptote as x goes to negative infinity. So what that means is as we look at our function and we travel, we're looking at x as it goes this way, our function approaches the x-axis. It never touches it, but it gets closer and closer and closer as we go farther and farther out to towards negative infinity. So that'll be an important thing to remember with in calculus if you discuss limits and things like that. And then finally, this function is continuous. So there aren't any breaks in it. There aren't any skips in the graph. It's very smooth, right? It goes going from left to right. It's a smooth function. So then let's look at the other case, the a to the negative x. And so the domain is the same. All real numbers here again. The range is also the same. It's still from 0 to positive infinity. Again, it never crosses into that negative zone. Our intercept, our y-intercept is 0, 1 once again. This function is decreasing. So going from left to right, remember we always read it left to right, it's always going downhill. So this function is always decreasing. Here the x-axis is a horizontal asymptote as x goes to positive infinity. So this time we're looking at it going this way. And going to the right, our function gets closer and closer to the x-axis, but it never touches it again. So yeah, once again, it's a horizontal asymptote, the x-axis is. Again, this function is continuous. We don't have any breaks in the graph. We don't have any skips or jumps. It's very smooth. And then this graph is a reflection over the y-axis of f of x equals a to the x. So yeah, if you take a look at both of these graphs, you can see that if we flipped this graph over the y-axis, we get exactly the other case. So now that we have a better understanding of these exponential functions, why don't we take a look at what transformations we can do to their graphs. So they work largely the same as transformations that we've seen on other graphs or other functions we've studied. So first we can take a look at shifts, shifting horizontally, vertically, and the like. So f of x equals a to the x, that's the graph that we've been studying. If I want to shift this graph horizontally, I just have to mess with my x coordinate, essentially. So I can do f of x minus c, right? And depending on the sign of c, that's going to shift my graph either left or right. So left or right by c units. And it all depends on the sign of c. And I'll give you some examples in a little bit here. But let's also show how we can do a vertical shift. So if I want to shift vertically. If I want to shift my graph vertically, I don't do it in the x-coordinate, I do it outside. So plus d or something like that. So then I'll have a to the x plus d. And that's going to shift me up or down by d units. And again, depending on the side of d. We can also look at reflections of the graph f of x equals a to the x. And so if I want to reflect over the x-axis, I have to make my f of x the opposite sign, because that will take me into like negative values essentially. So this will become negative a to the x. And like we saw in our earlier problem, if I want to reflect over the y-axis, I change the sign of my input, my x here. So that's going to make this a to the negative x, which is exactly what we saw with our other problem. The reflecting the 2 to the x over the y-axis gave us 2 to the negative x. So let's go ahead and take a look at an example of what shifting an exponential graph looks like. So if I take the graph f of x equals 2 to the x, the one that we've been looking at, we remember that it looks something like this over here. So let's say that I wanted to graph f of x equals 2 to the x minus 1. Well, understanding what that does, we can we know that this wants to shift this graph by 1 to the right. Okay? So I like to orient myself, let's pick a different color maybe, using the point that we know, that y-intercept here. We know that we always have this point, 0, 1. So if I'm drawing the graph of the same function but shifted by 1 to the right, that's kind of the point that I can use to orient my new graph. So instead of 0, 1, I'm shifting it by 1 to the right. So I'm now going to have that point at 1, 1. And then everything else should just look the same, essentially. We're keeping the same shape of the graph, so it has to look something like this. And you can see it's kind of just scooched over to the right. Okay? And if I had 2 to the x plus 1, that would just take me 1 to the left instead. So that's how the horizontal shifts are going to work. Let's do a quick sketch of the vertical shift that we have here. Do that one in blue. F of x equals 2 to the x plus 2 on the outside here. So that just takes my graph of 2 to the x that I have up here and scooches it up by 2 units. So instead of 0, 1, I'll have 0, 3. And this one can be a little bit trickier to visualize. So notice going to the left here on my graph of 2 to the x, I approach the x-axis, so like it extends out and my function will never touch this line, right? So I have to shift this asymptote up as well, essentially. So I'm shifting that up by 2 units. It's at the line y equals, it's ugly, y equals 0. So for this one, I'm going to have a horizontal asymptote at y equals 2, because I have to shift it up. So let's plot 2. Where would that be? Like 1, 2, 3, like here. So this is going to be my new line where I can't cross it. And so it's going to go like this. Right? So doing this shift actually changes the range of values on my on my graph here. Notice now that the range is positive 2 to positive infinity rather than 0 to infinity. So next we can look at the graphs of these reflections of our function 2 to the x. So let's draw another plot here. I'll go back to green, I guess, for this one. Or maybe I'll do it in red again. So this one, the negative is on the outside. So going back to our rules, that's a reflection over the x-axis, right? Because it's taking my values and it's making them negative. So again, let's sort of centralize or like orient ourselves about that point that we have. And I'm going to extend our axis a little bit more since we're going into the negatives here. So remember we had that asymptote, or not the asymptote, that intercept 0, 1, right? So if I'm reflecting over the x-axis, that point 0, 1 is going to flip down here and become the opposite, 0, 1. And then looking back at this graph again, going to the left, I get very, very close to that axis that I'm reflecting over. So it's going to do a similar thing, just going the opposite direction if in our reflection graph. So I'm still going to be approaching the graph, or the x-axis on this side. And then I'm going to come out like this. Not a perfect sketch at all, but this is what the reflection would look like. And I'll quickly sketch what the original graph looked like. So, wow, I did that one so much better. Yeah, so you can see that reflecting over the x-axis just takes your function and throws it into the negatives. And so let's take a quick look at this other reflection here. We kind of did this one already too. And so this one is a reflection in the y-axis, right? So I can draw my original graph again. Let's try to do it nicely. Yeah, that one always turns out quite nice. And if I'm reflecting it over the y-axis, notice this time that our intercept is on the y-axis, so that one isn't going to change at all. I still have that intercept. But these points are going to flip to this side, and I'm going to have that sort of decaying graph, like this. So one more concept that I want to introduce to you guys before we do some applications and examples is the natural base e. And e is Euler's number. It's this irrational number, this never-ending decimal, 2.71828, etc., etc. And generally, or like typically when we look at applications that are financial applications, like interest and things, we don't look at 2 to the x or like 3 to the x. We look at this number e to the x. And so this number e was actually discovered from compounding interest. And I'll spare you the details on that, but there's a really good video about it by Numberphile, which I'll link in the description if anyone's interested. For now, let's just work on understanding how compound interest works. And so if you think of compound interest, like think of your bank account, like the number that you see when you open your Chase app or whatever. So that's based on the amount that you had in your account, the rate that they're giving you, the annual interest rate basically that the bank gives you, how long it's been in there, and the number of times that your amount is compounded per year. So we have a nice formula to calculate that. A equals P times 1 plus R over N to the NT power. So let's take a look at each of these letters. So A is the account balance, essentially. So that's the calculated amount. That's what you see when you open your Chase app. T is your initial investment. So the amount that you started with in your account, whatever you deposited. The, I'll say initial investment. And then R is the annual interest rate. So the rate that the bank gives you, essentially. The annual interest rate. N is the number of times that your balance is compounded per year. So number of times, let's see, how do you want to say it? I guess balance. So if it were like monthly, you'd have 12. If it were every 6 months, you'd only have 2, because that's how many times per year, right? And then T is just the amount of time in years. So amount of time you've had your investment in there. So that's compound interest, with N being the number of times the balance is compounded per year, where N is some number, some fixed number that we can like plug in. But we can also have what's called continuous compound interest. And that's where our number E comes into the equation. So if we were trying to calculate it, like at every second of every possible day, there's no way we could figure out what that N number would be. So instead, Euler's number can be used in the equation A equals P e to the RT, where we have the same definitions for our variables here. A is the account balance, P is our initial investment amount, R is the rate, and T is the time in years. All right, so now let's take a look at an example so we can get some practice plugging in the values into these formulas, this compound interest and this continuous interest. So you invest $6,000 at an annual rate of 4%. We want to find the balance after 7 years when the interest is compounded, either quarterly, monthly, or continuously. So let's first take a look at quarterly compounding. So here, we first need to know what equation to use. We're not doing continuous, right? It'll tell you if you need to use continuous in the problem. So we're using quarterly here. So we're going to use the A equals P times 1 plus R over N to the NT. So let's just copy that down first. Okay, and we want to calculate the total amount after 7 years, right? So we're finding A. We want to find A. So that's going to be the variable that we're not plugging anything in for. We're solving for that, right? So let's plug in everything else that we know. P is the initial investment that you make, right? So that's going to be our 6,000 here. And then we have 1 plus R was the rate. So 4%, we need to write that as a decimal, so we'll do 0.04 divided by N. Now, N, we need to figure out what it is. So because we are doing quarterly, you need to ask yourself, how many quarters are there in a year? Well, there's 4, right? So our number N is going to be 4 here. And then we're plugging in 4 again for this N here. And then T is the time in years, so that's going to be 7 years. Okay, so this is what we're trying to figure out here. And at this point, it's really important to make sure you have your order of operations down. So we need to solve what's in the parentheses first, and then take this exponent, and then multiply by 6,000. That's the order that you want to do it in. So we'll leave the 6,000 on the outside for now. And then if you're plugging it into your calculator directly, I would just start with this fraction here, this 0.04 divided by 4. And so if I calculate that, I get, keeping the 1 the same, plus 0.01. And then we can resolve this exponent a little bit too. 4 times 7 is 28. So this is what we're working with now. So again, let's leave the 6,000 on the outside. We'll now simplify further in the parentheses. 1 plus 0.01 is 1.01 to the 28th. So now you want to calculate this 1.01 to the 28th. So let's go ahead and do that. 1.01 to the 28th power. And so once you have that in your calculator, you'll have some pretty long decimal that I don't want to write down here because you could lose some of the decimal numbers and lose some accuracy. So at that point, once you have this number, go ahead and just multiply it by 6,000. And then that will be your final answer. You want to round as little as possible, like until the very end. If you can avoid rounding until the very end, then you'll have the most accuracy. So this is what I get, and this is dollars. So because it's dollars, you want to round to 2 decimal places. So that's what I get from quarterly interest. So now let's do part B, where we do monthly interest. And it's monthly again, not continuous, so we're still going to be using the same equation. A equals P times 1 plus R over N to the NT. And again, we're going to be solving for A. We have 6,000 as our initial investment, times 1 plus, the rate should be the same, so that was 4%, right? All right, now I need to figure out our N once again. So this one is monthly. So you ask yourself, how many months are there in a year? Well, 12. Hopefully we can all do that part. Just make sure you do this step so you know, like that's how you figure out your N value here. So 12 months in a year. We plug that in for both of our N values. And then T again is 7, because we're looking at this value after 7 years. So again, let's go ahead and simplify. I leave the 6,000 on the outside. Simplify within the parentheses first, so I always attack this fraction first. I just plug it into my calculator, figure out what that is. It's kind of an ugly decimal in this case, so let's go ahead and add the 1 right now, where we're at. So I get 1.00, and then it's 3 repeating. So I would just leave this number in your calculator the way it is, so that you can continue to work with it. We can simplify this 12 times 7, that's 84. So next, we're going to want to take this 1.003 repeating to the 84th power. So go ahead and do that. And then again, I have a long decimal number. So at this point, I will just multiply it by the 6,000 to avoid rounding until the very end. So I would advise doing this yourself at home also, so you can check and make sure you're getting the answers that I'm getting. But I get 7935.08 if I'm rounding to 2 decimals. So we can see that this monthly compounded interest is a little bit more than our quarterly compounded interest, right? So let's see what happens if we do continuous now. So continuous, I need to use my other equation, a equals p e to the rt. And your calculator should all have this e button somewhere on there. You'll just have to find it. So again, we're solving for a. We have the same initial investment of $6,000. We don't need to do this calculation here, this 1 plus r over n, because we have e now. So just leave it as e. And then e to the rt. So r, again, is 0.04. And t is 7 years. So this is a much simpler calculation, actually. It's nicer. But again, let's tackle the exponent first to do correct order of operations. So find the e button on your calculator. It's usually e to the x. And then it'll give you e to the power, and you fill in what the power is. So you can do e to the 0.04 times 7. That'll give you some decimal number. And then just multiply by the 6,000 while you're there. So I get 7938.78, rounding to two decimals. So it looks like the continuous actually gives us the highest amount of money made. Alright, so let's finish with one more example. We have the number of a type of bacteria increases according to the model. P of t equals 100 times e to the 0.01896 t, where t is in hours. And we want to find p of 24. So what does p of 24 mean exactly? Well, t is in hours, so we're looking at the population, p, after 24 hours. So we're looking at how much the bacterial population grows after a day. I always think these ones are really interesting because bacteria multiplies like so quickly. So let's go ahead and take a look at that. P, 24. All we have to do is plug in this value for t. So this is quite a straightforward problem. So 100 was given to us. We can recognize this as the continuous, like compounded, not interest, I guess here, but continuously compounded type of equation. So we started with 100. That was our initial population of bacteria. So 100 times e to the 0.01896 times 24. So definitely a calculator problem. I would start with e to the whatever. E to the x is usually the button on your calculator, so you press that. And then just plug in this 0.01896 times 24. And then once you have that number, let's see, we have this whole thing calculated here. So all we have to do is multiply that by 100. So let's go ahead and do that. And so I find that p of 24 is 157.62. I tend to just go to two decimals. It'll if someone wants you to be specific, they'll tell you how many decimals to round to, but we can see that after one day, our bacterial population has increased by like 57 new cells have emerged, right? So that's how you would interpret this problem here. Anyway, that was the last example that I wanted to cover today. There are other types of applications for science models or like financial models for these kinds of equations. So yeah, I guess I will see you guys in the next lecture on Thursday.